This project is entitled Leak Detection in Water Distribution Systems, a supervised learning technique on acoustic sensor data, and I'm Mohsen Agha. Leak is an important problem for water utilities. It causes lots of water and financial losses. One approach to solve this problem is installing hydrophones on fire hydrants and acquiring some acoustic data and then use them and implement some classification methods. In this project, we convert the raw data acquired from hydrophones. We convert them to time and frequency domain signals, and we extract features to build a data matrix where it has 398 rows and 9 columns, where columns are features. And then we use the data matrix for PCN and heat map analysis. And finally, the data matrix will be used for fitting a logistic regression in addition to cross-validation, where evaluation metrics are ROC curve and F1 score. And finally, the classifier will be tested with new test data. The AI approach is a supervised classification because our acoustic signals were labeled either leak or no leak by experts, and the features which are extracted from these signals are time domain features, which are variance, mean, median, 25 and 75% percentiles, or frequency domain features, which are frequency, amplitude of peak frequency, centroid frequency, and energy. The input to the classifier is labeled data, and the output is the equation of a classifier with large F1 score and low false negative. With the algorithm that we use is logistic regression as a supervised learning, because James et al. Recommended this algorithm where we have well separated the data, and also it is very well apprehendable. As it was mentioned, metrics for evaluation are F1 and area under the ROC curve. The training data is at 398 totally, where 48 are leak and 350 are no leak, and 100 data which are unlabeled will be used for tests. Both training and test data has 8192 hertz of frequency. And the length of the data of each signal is 2 seconds, and the plot of time series signal shows that the leak data is denser than no leak data. And also the histogram, the right side of this slide, shows that amplitude of leak data is more variable than that of no leak. The left side of this slide shows the heat map, where centroid is the most independent feature, and 25 and 75 percentiles are highly correlated. The right side figure shows the PCA analysis, where the right part of the PCA figure shows that two principal components preserve more than 90% of variance of features. And the left side of the PCA figure shows that the data are well separated. The table of F1 score shows that F1 score for different fold cross validations are quite large, where then F1 score for class 0 is larger than class 1, and the left side of this slide shows the confusion matrix for 5-fold and 10-fold cross validations. When we plot the F1 score and number of folds, we see that when we increase the number of folds, the F1 score for class 1 increases much larger than class 0, and that is due to the number of data. Since number of data in class 1 is much less than number of data in class 0, it shows that classifier is more vulnerable to data selection with changes in cross-validation iterations. And this is the area on the ROC curve for 5-fold and 10-fold cross-validations, where the area for both are large. And the significant features as an output of classifier are frequency of peak amp, 25 and 75% percentiles. We recall from heat map that the percentiles were highly correlated, so we dropped one of them. We dropped 25% percentiles, so we reached to this figure that frequency of peak amp and 75% percentiles are the most significant features, and their coefficients, where F1 score didn't change. So finally, the classifier would be like this. The left side is the logit, and the right side are features and their coefficients, where P of x, the probability that signal x is leak, x1 is frequency of peak amplitude, and x2 is 75% percentile. And fitting the classifier on the test data, new test data shows that area on the ROC curve is quite large, and also F1 score is large, though the classifier performs better for class 0 rather than class 1, and that is due to the larger number of class 0 with respect to class 1. Some takeaways are that both time domain and frequency domain features are important. We recall that frequency of peak amplitude is a frequency feature and 75% percentile is a time feature. Amplitude variability in leak signal is more than that in no leak signal. We recall that from histograms. The more data set we have, the better training and performance in test step. An increase of number of falls in cross-validation does not change evaluation metrics significantly. And the most important one is the logistic regression with cross-validation works well in a classification problem with highly imbalanced data. In the future, we will evaluate different classifiers and other features of pipelines, and these are the references.